view, I will, despite the fact that now I'm thinking about codes differently, I nevertheless want to start with some history, because if you care to look at my papers which are already out, you might start seeing completely different story from what I would like to tell you today. So the story is actually an old one. It started 30 years ago by this group of very well known string theorists. And more like 4 years ago, we revived that story. And the story is about an ad hoc connection when you start with classical codes and you construct some lattices. And when the fact that you can start with some codes and construct some interesting lattices, this is not a new story. This is not a story initiated by physicists. It's very well known by discrete mathematicians. There is this very famous book, which is a collection of articles called SPLUG, Sphere Packings, Lattices, and sure what else. Back in the 70s, people understood that codes of very special type can be connected to very special lattices, and those have very interesting properties, in particular in the context of sphere packings. 30 years ago, this observation was leveraged to do some interesting physics. 5 years ago, we realized that there's more to do, and we did quite a bit of progress in that direction, but that was an ad hoc. There was no physical roots of that construction. About 6 months ago, we realized that there is a very clear connection between codes and topological quantum field theories, or physics of physics of anyons. That might be the best way to put it. So when we think about anyons, just think about toric code. And then this connection is very similar to holographic connection, because the toric code is a two-dimensional system, but it has time, so it can be understood as both two-dimensional, three-dimensional in a proper sense. That smells like holography, but not quite holography. And then actually to make a holography, you need to do additional parts of the construction, which also very naturally fit in this perspective. And that's the way, that's the step which you need to go to start from the classical codes and end up with the quantum codes. So to go and describe holography, you actually need quantum codes. So today I will end my presentation with quantum codes. Yes.
So the dimensions already seem a bit mismatched. The toric code is defined on 2D lattice of qubits.
Correct. But it has time. So as a quantum field theory, it's a 2 + 1 dimensional quantum field theory.
So 3D means 2 + 1.
Of course. That's always, yes. The language, yes, sorry, that's another cultural difference. 2D is space and time, and 3D means space and time. Quite often time is Euclidean, so you don't even distinguish between time and all other spaces. So that's a one-dimensional CFT, like on a circle. Circle is a space, and one dimension is the additional dimension is time. Here you have two-dimensional space and time. And as Victor mentioned, there are holographic codes, maybe happy codes, maybe many of you heard of them. Our codes may be in some bigger sense more related to them, but that's yet to see in the far, far future. There is no direct relation at this point. And one reason is because in our case, in 3 dimensions, we have topological quantum field theories, and they have genuine gravity. And there is a difference. Genuine gravity knows about distances, like we know about distances in our physical space. Topological quantum field theory only knows about topology. You can morph things continuously in any way you want. So physically, this is different, and therefore our codes much simpler than happy codes. But there might be moral relation 5 years later on or something like that. Okay. So to start the story, let me give you a very brief introduction how lattices might be related to CFTs. We will start with very special CFTs, free scalar in 2 dimensions. So you have 2 dimensions again. It could be Euclidean 2 dimensions. Usually Z is a coordinate on a torus, and phi is a scalar field, and it's compact in the sense that phi is equivalent to phi plus r. And then your z coordinate should be understood as a complex coordinate. There is z and z bar. For laziness, I'm writing only z. Phi is not a holomorphic field. It depends on both z and z bar. As a function, it's not holomorphic. There are versions of this when it is holomorphic. This is not holomorphic. And it's defined on the torus with a modular parameter tau, so their periodicity with 1 and tau, complex parameter. And then you can have windings in both directions. So an arbitrary configuration of phi field is parameterized by two integer numbers n and m. There are windings along the space dimension and time dimension. When you try to solve this as a classical field theory, and there's nothing quantum about it's quantum, but there's nothing really quantum about it because it's quadratic. It's a free field theory. Free field theory, quantum, and classical is essentially the same thing. To quantize, you find all classical solutions, and then you promote coefficients to be creation operators. You will see that there is a lattice which is mixing both moments and windings, and this lattice is described by this a pair of integer numbers. Morally speaking, this n and m are this n and m. Morally speaking, or more accurately, there is a relation between this n and m and this n and m. This pair of vectors PL and PR form a lattice in 2 dimensions. This lattice has very nice property. It's even and self-dual. If you heard of even subdual lattices, maybe you heard that they only live in dimension divisible by 8, because those lattices are with the Euclidean norm. Our lattice is in a space with Lorentzian norm, n, n. In this case, n is equal to 1, so it's 1, 1. If you have non-Euclidean norm, for example, n, n, then n could be arbitrary. More generally, if you have n and n bar, you have even subdual lattice n minus n bar should be divisible by 8. So if n bar is 0, n should be divisible by 8. Okay.
You should define the norm.
The norm I'm using here, well, since there's only one norm with a signature n, n bar, you can put it as n pluses and -1 and n bar minus ones. That's one way to do it. If n is equal to n bar, you can also put n pluses and n minuses, or you can put 0, 1, 1, 0. It's up to you. And they're mathematically equivalent. Okay, so what we need is the following statement. There is a class of 2-dimensional conformal field theories, which is essentially a generalization of this story, which are uniquely parameterized, defined in terms of even self-dual lattices in the Lorentzian space. Yes.
But how is PL and PR related to the field theory?
PL and PR are moments. So this is a so
like their expectation value?
no, they're not expectation values. They're not expectation values. Phi is a field which is not well defined because you can shift it by R. So phi is not even a good operator in quantum field theory.
Okay.
What is a good operator in quantum field theory is something like I phi, because phi is periodic,
Sure.
but it's not exactly periodic because it's shifted not by 2 pi by R. So what is well defined is something like PL multiplied by holomorphic part of phi plus PR multiplied by anti-holomorphic part of phi. Okay, that's morally speaking. And PL and PR are defined such that this thing is well defined. Okay, and these are proper operators in my conformal field theory. This is called the vertex operator. And PL and PR, the lattice of PL and PR defines this whole set of vertex operators called vertex operator algebra. It's a more mathematical, more formal way to define my CFT.
Phi is assumed to be able to be split into holomorphic.
Yes,
holomorphic
because it's a free field theory. You can explicitly write down the solution and then manually split it in the left hand side and right hand side. That's so easy because it's a free field.
So interacting ones don't have lattices.
Interacting, constructing, interacting field theories in terms of lattices, that's not possible.
Right.
There's a much more complicated structure. So all of these field theories I'm talking about today are free, but they're still rich. And if you try to calculate their partition function, for example, you will have very complicated theta series. Theta series like Jacobi theta function on steroids. Okay, so let's move a little bit. So now we'll try to review the story from the 70s that classical codes can be related to very special lattices. A classical code, let's say binary code, is a collection of strings of zeros and ones. I want to consider additive code, so you can add those strings together and get new strings. And a code is essentially a linear subspace that if you add two strings together, you get again a code word. Then there's this construction A. It's a famous story from mathematics that you can promote each code to a lattice. Basically, you consider a sublattice of a cubic lattice. All elements here, all these here are vectors in the real dimension, real space, but the coordinates are integer. You only consider integer valued coordinates. So it's a sublattice of a cubic lattice. And then you take V mod 2, it becomes a binary string. If as a binary string, it's an element of a code, that point belongs to a lattice. And then for some reason, which I don't want to explain, you rescale by square root of 2. That's the right way to do it. Sorry. That's the right way to do it. So that construction gives you a lattice based on a code. Not every lattice can be built from a code this way, but every code gives rise to a lattice. Now, if code is nice, for example, it's a self-dual code, the lattice will be self-dual. If code is nice, it's double even, the lattice will be even. For example, if you have a perfect Hamming 8,4,4 code, will have very special lattice. The only even self-dual lattice in 8 dimensions, a root lattice of E8. Okay, so that story may be heard of. That's a very famous story. This code, I hope you heard of this code. So that's one way to start from a code of a particular kind to build this lattice. This lattice is even self-dual. You can define a CFT. And then the CFT is very special. And that's what people started in the 90s. That's exactly what they did. This part mathematical was known well beyond that, before that. But defining a CFT with this lattice and studying its properties, that's more like late 80s, early 90s. And then if you go into 24 dimensions, where there are many, there are 24 even self-dual lattices in 24 dimensions. It's perhaps a coincidence. And then you use them, and then you do other mathematical tricks, and you define the very special CFT called the monster. And then the symmetry of the monster is the biggest discrete group in the world. That's called the monster group, I suppose. And that's a very big mathematical story behind it. So that's what people did in 80s and the 90s. We'll be doing something similar, but much simpler. So I want to visualize how you build a lattice from a code. The idea is that binary strings essentially by definition are vertices on a unit cube. So if you have a binary code, it means you have certain vertices, highlighted vertices on a unit cube. And the idea of a construction A is that you take this cube and you do the parallel transform with a step 2. Let's say your code has 2 points, 0, 0, and 1, 1. It means that you take those blue points and you move them in all possible directions with a step 2. I have that visualization, and I have yet another visualization on this slide. When you have a unit cube, which is inside the circle, you have 2 points here, and you move them in all possible directions with a step 2. And now you have a lattice of highlighted points, red and blue, and you see that the resulting lattice is not cubic. It's a sublattice of a cubic lattice, but it's not cubic. And with a little bit more imagination, you have more complicated codes. This code is a very simple one. It consists of 2 code words, 0, 0, and 1, 0. But if you have more complicated codes, which are very special and have interesting properties, you can have truly non-trivial lattices. And then you can use them to build interesting CFTs, and that's what we played with 4 years ago. Yes?
Why is it 2 here? How come you can't just shift it by 1?
Why not by 1? Because if you shift it by 1, you will not have anything nice. Because if you shift 0, 0 by 1, it will be again the whole cubic lattice.
Oh, I see.
Okay, that's why you have to shift by 2.
Thanks.
Okay, at least I gave you a flavor of this game we played, but there is another algebraic part of it. You want to be interested to calculate what is called partition function of a CFT. Partition function is the main object which defines the physical system, at least if you are concerned with the statistical physics. And to calculate the partition function, you basically need to enumerate all vertex operators. For that, you need to know all vertices of a corresponding lattice. And that's exactly what lattice theta series does. Okay, and to calculate that, apparently, if your lattice came from a code, you don't really need to work hard. You don't really need to worry about the lattice. There is this beast which characterizes the code itself. It's called enumerator polynomial. It's a very simple thing. It's a polynomial which keeps track of how many different how many different lengths of the code enumerator polynomial is an information of how many code words of particular length your code has. Each code word, you can calculate the length or Hamming weight. And then if you calculate how many code words of a particular length you have, this is called the spectrum of the code. So the polynomial just incorporates that information and nothing else. It's a polynomial. And then if you take this polynomial and plug into, instead of formal variables, certain Jacobi theta functions, you will have the theta series of a corresponding lattice. And then if you multiply it by another very special function, which is called Dedekind eta function, you will have a partition function of the whole CFT. So that completes the part of the story when you want to calculate CFT partition functions starting from the code. Any questions? Okay, so that's the story. You have the enumerator, then you calculate theta function, then you have a partition function. But partition function of a CFT is a very, very special object. It's modular. If you have a CFT living on a torus, you can make what is called modular transformation of a torus. There's a geometric renaming of the cycle of the torus. There is a special group which does that. It's a symplectic group. Well, in case of a torus, it's a symplectic group or equivalent to SL2. If you have a Riemann surface of genus G, it's a much bigger symplectic group. And this object has to be invariant because geometrically nothing happens with your torus. You simply rename different cycles on the torus. Or if you wish, you introduce different coordinates. That's a little bit less mathematically precise, but morally that's good enough. So nothing should change, and the Z should be invariant. Mathematically, this is highly non-trivial. But if you start with a polynomial, it basically will be incorporated in a polynomial because the numerator polynomial of a code usually satisfies if the code is special, if it's self-dual, it not usually, it always has to satisfy certain algebraic identities called Mach-Williams identity. And in a theory of code, it's very well known. It's something like a discrete Fourier transform. And if your polynomial satisfies this identity, it guarantees that corresponding Z obtained through this formula will be modular invariant. So that's already gives you a lot of mileage because solving modular invariance, imposing modular invariance, that's mathematically highly non-trivial. Imposing algebraic constraint on a polynomial, that's a much easier thing. You have a polynomial of one or two or three variables, and you simply want that polynomial to satisfy some very straightforward algebraic identity. You can check that easily. And that guarantees that this partition function will obey certain non-trivial mathematical properties.
So just so I don't lose you, the binary code properties can be related to the CFT properties via the construction name mapping via the lattice, basically.
Yes, absolutely. Because the CFTs we consider, they're actually defined in terms of the lattice. So we have to go through the lattice to make this connection.
There's an assumption here that the binary code properties are somehow preserved when going to the lattice and then go forward.
It's not an assumption, it's by construction.
Okay.
If you have linear codes or additive codes, when you add code words together and you're still within the code, it naturally wants to be a lattice because lattice is also closed under addition.
Yeah.
And that's how you build the CFT. If you want to do a more general CFT, then likely, we don't know how to do it, but likely the codes will not be additive. And then the story will be much more complicated. And we are not ready to speak about this story yet.
Yeah, can you just go back and clarify or say more about, so the codes that you're studying are all small codes within the lattices, I guess.
Yes.
So
Small, what would be a small?
Well,
certain length?
yeah, their length.
The length of the code is what you want, let's say it's M. And this length will be the dimensionality of the lattice.
Okay.
So let's say you have codes of length 2, so there are only 2 bits, 0, 0, 0, 1, and so on and so forth. It means that points, the code words of this code are vertices on a square, and that square will tile to dimensional lattice. Using this construction A, which is essentially taking a unit cube and moves it in all directions. That's step 2.
So what settings do we care about, like very large dimensional lattices?
It's up to you which length of the code to consider. But in information theory, you're interested in considering large n. Is that what your question?
Well, yeah, information theory, we care about large n, but in CFT, do people care about?
Yes, yeah, that's a lot. I'm answering your question. Yeah.
Just let you go.
No, I want to answer your question. This is a slide about our achievements. What did we achieve in a practical sense, starting with this construction? So, morally speaking, you can make it a precise statement, but then it has to be a little bit nuanced. But morally speaking, the code with a larger Hamming distance, so a better code, will give you a CFT with a larger spectral gap. A spectral excited state in your CFT. Okay? You can say, how is that possible? CFT is a conformal field that has no massive particles. What am I talking about? I'm talking about a state, not a particle. My CFT is living on a compact space. Therefore, all states will be dimensionless numbers divided by the volume. Volume, there's nothing I can do with this, is a homogeneous factor, but that dimensionless number is what I care about. And I want that number to be as large as possible. And in physics, we are very interested in CFTs with large spectral gap, because if you try to describe dual quantum gravity in terms of CFT, there is a very long story, very rich story that you should have CFTs with very large spectral gap. And that's why considering better and better codes in the information theory sense makes you closer and closer to understanding quantum gravity. And in fact, this connection is very rich. And in the context of codes, people use linear programming bounds, de Lassartre linear programming bounds. This is essentially a coding counterpart of what people call modular bootstrap. And when people try to use the Lassartre bounds to bound the Hamming distance of a code, the analog of that is that people try to bound the spectral gap in a CFT. Okay, and this is, in some sense, this is an analog, but in certain contexts, you can literally start with a modular bootstrap and reduce it to de Lassartre's bounds, or you can reduce it to Cohen-Elkes bound on sphere packing, which is another avatar of the same story. Okay. So what codes can help you do? They help you solve the modular bootstrap constraint. Modular bootstrap constraint is a constraint that your partition function is invariant under modular transformation. Mathematically, this is a highly non-trivial constraint, but from codes, you get it for free. And you can construct many solutions using codes, or very special solutions, for example. You can consider isospectral theories. That's when you have, what is an isospectral? Let's start from the old story. There's this famous paper. Can one hear the shape of a drum? Mathematical question is very famous. If you have a Laplacian on a compact manifold or manifold with a boundary, is it like a drum? Right? Drum is a manifold, two-dimensional manifold with a boundary. Is it possible to completely decode the geometry of that space from the spectrum of its Laplacian? So you hear the drum, you have the spectral analysis, you know all the modes mathematically from 0 to infinity. Is it uniquely telling you the shape of a drum? The answer is no, and there are counterexamples, and the counterexamples are very simple ones. You can consider two different multidimensional tori, which will have exactly the same spectrum. The multidimensional tori, the spectrum of Laplacian is the same as the lattice. That's a simple, I will not explain it, but that's a simple thing, that the Laplacian on a torus is a lattice, is related to a lattice. So we need to consider isospectral lattices. And people constructed those isospectral lattices, I don't know, back in the 70s, 80s. But those lattices were in Euclidean space. If you consider Lorentzian space, we produce many more isospectral lattices, many more. Hundreds, thousands. It's a machine which generates as many of them as you want. And those isospectral lattices give you isospectral CFTs, which means that physically two different conformal field theories, you calculate their torus partition function exactly the same. Okay, so that's already some very explicit result. We published this paper in 2020. 2 years later on, we published another paper where we constructed what we call fake Z. What is the fake Z? It's a function Z, which is modular invariant, and it looks in all possible senses like a partition function of a conformal field theory. But then you can go and prove that this is not a partition function of any conformal field. So it's a counterexample which shows that mathematical consistency of a torus partition function is insufficient to really distinguish between partition functions of genuine theories and just fake ones, which you can artificially prepare. And then, as I already mentioned, there is a connection to this linear programming bounds, the Sartre bound. Okay, so this is what we achieved so far. That's an old story. I used 30 minutes, or maybe a little bit more, half of my talk. That's an old story. There is a connection between classical codes through lattices to CFTs. If you're interested in classical information theory, sphere packing, there is something to discuss, something to do even now, because many of these questions were formulated decades ago, still not solved. Now I want to tell you a more recent story about holography and the relation between Chern-Simons and conformal blocks. But I'm not sure if I should dwell on this, because if I start telling you the story, we can start getting stuck maybe. So maybe I'll skip this slide. Let's see what I have here. I want to start with this slide, because this slide is an example of the previous one. And this is Kitaev's story code. So this is hopefully the common ground we'll have. And let's use this example. For me, Kitaev's story code is when you have two-dimensional system, and I don't care how you implemented it, what are the plugins, I don't care. I only care that it's a double periodic, so it's defined on a torus. You also have time, which is going in that way, if you wish. And then the ground state is 4 times degenerate. Not only that, you have what is called anyons. You can think of them as actual particles, which are very massive. But you can also have closed loops of anyons. And I do not know really how to explain that from the condensed matter point of view, but from theoretical point of view, it's an operator in the theory. It's a Wilson line operator in the theory. I'm not sure, I need to read a little bit more reviews on condensed matter, how people motivate this in condensed matter context. But if you have an anion and you have a closed loop of anion, it becomes from the coding point of view, it's a logical error. Actually, I remember now how this is explained. You have 2 anyons, they're separated, very heavy. That's why that's why Tori code protects quantum information very well, because you need a very heavy excitation. But if 2 anyons meet again, it becomes light again, and it produces a unitary transformation in the logical space. So it's a logical error. So from our point of view, it means that you have 2 qubits, and each closed contour gives you an operator. And there are 2 types of operators. There's electric and magnetic, and there are 2 cycles on the torus, red one and blue one. Red one is called A cycle, and blue one is called the B cycle. Okay, all good? And then we can just say that electric over red cycle is the Z Pauli matrix, and then Z over this, and that's a very explicit dictionary, okay, between the different cycles and different anyons, and Z and X Pauli operators acting on 2 qubits. Besides E and M anyons, you can have an F anion, which is a product of those 2, but that means that instead of Z and X, you will have a product that will be a Y Pauli matrix, so it's redundant. We don't have to discuss it here. Okay, so what do we want to do with the Tori code? Well, with the Tori code, I want to consider certain quantum codes within the degenerate ground state of the Tori code. I have 2 spins. And I will use them to prepare very simple stabilizer states. I will do that I will give first the physical motivation of what I want to do. I want to take an E anion and I want to condense it. What does it mean physically to condense it? Well, there's a much better physical explanation what it is, but from the logic of the stock, to condense an anion, it means that the corresponding operator should be a trivial operator. And it should not matter for me whether I wrap it over A cycle or B cycle or any other cycle. If I have an E anion, I want a closed loop of E anion to act trivially on my state. That state will be a particular state of 2 qubits. So now you can realize that what I'm trying to do is prepare a certain stabilizer state, because I have two basic loops of E anion over E cycle and over B cycle, over A cycle and over B cycle, over red or blue cycle. And I want both of these operators to act trivially on a particular state. So essentially, by definition, I'm preparing a stabilizer state. So the stabilizer state is this one. This is a stabilizer state of the E anion. It means that this is a state on which the anion, E anion is acting trivially. And I will say that I condensed E anion. Okay? This quantum code, you can see, and we will see it later, it's not just a stabilizer code, it's a CSS code, which is produced from certain classical code. Okay, we will see that later. Maybe you'll already see it, but we will see it later on. Any questions about this?
Just to make sure I'm understanding, if you were to condense both E and M, you would just get a single state.
That will not be possible because E and M mutually do not commute. So you cannot simultaneously condense them, which means that you cannot build a stabilizer group which includes both E and M.
Okay.
You might include E and M over certain cycles, but not E and M over all cycles. So that's the question, what can be combined in the stabilizer group? But taking E by itself over all cycles is completely fine. Taking M over all cycles is completely fine. Taking F is not fine because F is not bosonic. If it braids around itself, it becomes -1, and it means it cannot be condensed. You can prepare a state of the corresponding kind, but I'm not interested in that state because F cannot be physically condensed. Now, I will tell you something which is not a part of the standard lore. I do not know if it was known to, maybe it was known to experts in some way, but it's not found in the literature. It's mostly can be read between the lines of our recent paper. But if you consider those two states in the toric code, the electric state and magnetic state, meaning that E anion is condensed and M anion is condensed, you can think about corresponding state as a wave function on a torus. A wave function on a torus is a holomorphic function of a particular kind. Well, actually, it's not sorry. The standard law should be that it's a holomorphic function of a particular kind, but the toric code has two fields A and B, so it's not a holomorphic function. That's important. I'm going to have a false speech why this is non-trivial, but I'll skip it. It's not a holomorphic function, but it's a wave function. And the non-trivial thing is that it's actually a partition function of a compact CFT, which we already saw in the beginning of my talk. I believe this is not very well appreciated by the community, although some expert might tell you that we knew that decades ago. So I want to emphasize because I think this is crucial for what follows. If you have the conventional toric code and you prepare two states by condensing E anion and M anion, and this is as simple as preparing two stabilizer states, and then you look at these states not as qubit state 0 and 1, but as actual wave functions, and you evaluate this wave function using this relation between a relation which condensed matter physics uses in the context of quantum Hall, so it's well mathematically well defined. You will have two partition functions of two CFTs of the kind we saw in the beginning of my lecture. One will have radius r divided by square root of 2. Another will have radius r multiplied by square root of 2. Okay, so this is a radius of first theory. This is a radius of another theory. In other words, these are two different CFTs. Yes.
Yeah, I think you're sweeping something under the rug here.
Yes.
On one hand, I have a many qubit wave function. It's just a sum of stuff. The ground state, it's a particular ground state, right? Psi of E is a particular ground
Yes.
state,
Yes.
defined on C to the 2 to the n.
Yes.
And on the other side, you got some R's and you got a tau and you got a whole different ballgame going on. So how are you connecting these?
Good. Good. So you're worried that Kitaev's toric code is a physical system with many qubits, right? Is that what you worry about?
Yeah, you're connecting those somehow to these
Right.
other things.
So there is a rather standard part of the story that low energy physics of Kitaev's toric code is Chern-Simons.
Okay.
And if you try to calculate the wave function, so this is really an old story in condensed matter. And if you try to calculate the wave function of Chern-Simons, it will be something like a CFT partition function, but not quite. And that something is called conformal block. So this is some holomorphic function which depends on tau. So basically, when you go into low energy physics, you forget about all of these qubits which made your system. You really only remember about topological property because Kitaev's story is topological. And the only topological property is the geometry of the torus tau. You don't even need the size of the torus. You only need certain ratio of the cycles of the torus. This is a modular parameter. And it's not even the geometry of a torus. This is what is called complex structure of the torus. And then a standard part of the story in condensed matter is that you will have something which is called conformal block. And all four states in Kitaev's ground state will correspond to different conformal blocks, so there are combinations. And that is very well known. There's nothing new about this. You can open any review about Chern-Simons in the context of quantum Hall, it will be written there. What is new is that if you consider a particular state, which is a stabilizer state of condensed E-anion, those conformal blocks will combine specifically in the way that the result is a CFT partition function.
But the psi E at the top is not the same as the psi E at the bottom. Psi E at the top is a digital version.
Quantum mechanically, this is a four-dimensional, this is the Hilbert space, and this is a four-dimensional Hilbert space. They're different representations of the same. Very different, because this is a function of tau, and in fact, as a function of tau, it's a highly non-trivial function of tau. It's modular invariant. It's a bunch of Jacobi theta functions, if you want to be exact. It's as a function of tau, it's very, very non-trivial, but there are only four of them corresponding to 0, 0, 0, 1, 1, 0, 1, 1. You combine them exactly in this way, and you have a CFT partition. Okay, so it's a different representation, but it's not an ad hoc representation. There is a way to motivate that. And the only way I know to motivate it is through topological quantum field theory. It's not something very complicated. The idea is that topological quantum field theory means that nothing depends on the size. So if you have a path integral of topological quantum field theory on something three-dimensional with a boundary being two-dimensional, by essentially geometry of that path integral with the boundary condition is a wave function. It's not different from, let's say, one-dimensional quantum mechanics. Like if we first go back to the famous textbook by Feynman and Gibbs, which explain to us what quantum mechanics is through the lens of path integral. In conventional quantum mechanics with one dimension, what is psi of x? Psi of x is a path integral over all possible paths, and you have an action of a classical particle. And then you say exactly that all of your paths x of t final end at that point. So that's exactly that's the wave function, right? And that's a Feynman-Gibbs story. If you think about this and then look at this picture, you will immediately conclude, at least at the level of a cartoon, that path integral of three-dimensional topological quantum field theory is a state. Now, in this picture, this is two-dimensional space and time goes like that, but mathematically you can make time Euclidean, so it doesn't really matter where it goes. So this is time going in this way. This is your two-dimensional torus where Kitaev's story code lives, and therefore there is a very clear mathematical way how to define that, and then this representation will be mathematically non-trivial. For example, if you do geometric transformation of a torus, nothing should change, or rather, a state should go into another state. That's maybe more proper. And therefore, there is a modular group which acts on those four qubits and maps them into each other. And from the point of anyons, this is a geometric transformation of the anyons. There is this famous S transformation of anyons. That's exactly when you rename A cycle into B cycle and B cycle into A cycle. That's exactly S transformation of anyons. So all of that has counterparts in the anyon physics. Okay, so this is the story code. So, okay, so now we are back to where we were, but on a completely different level. These are still the CFTs I discussed. Before that, I started with the classical codes, and I mapped classical codes to here through the lattice. Now I have a completely different story. What happened? How is different that story? The story is actually related to the previous one. I start not with the quantum code. I actually start with the classical code. I'm not writing it here, but I should maybe. I have a classical code consisting of two code words like this. I have two codes, this one and this one. These are two classical codes. And if you use the metric like this, those two codes are even and subdual with this metric. These are classical codes. I use these classical codes to produce a CSS quantum code by stacking them all together, and that becomes a symplectic code. And at the level of quantum codes, these are these guys. So 1, 0 is this guy, and 0, 1 is this guy. Okay, and I stack them together. So now I have a quantum code. Now I'm looking at the stabilizer state of that quantum code. It's a self-dual code, therefore there's only one-dimensional code subspace. And that wave function, stabilizer wave function, is the CFT partition function. So that construction is a complement of what I had before. I started with the classical code, I go into quantum code, I return back to a CFT, or I can go through a lattice. That's all part of the same construction. Okay, I have a few slides explaining the same thing with the toric code in the language of Chern-Simons. I do not know if that will be helpful.
Yeah, I mean, I think what you said was clear, except that this parameter tau.
Yeah.
I mean, that has there's no way of setting tau for construction. Right?
Tau is not a property of a CFT. Tau is a geometry of a torus on which you put your CFT or your toric code. In fact, you can put a toric code on a high genus Riemann surface. Then instead of 4 qubits, there will be more qubits. And instead of, it will be exactly the same CFT, but instead of a torus partition function, it will be genus 2 partition function. So this tau can be changed in any more complicated geometry you want.
But is there a way to change it if you only go through this person?
No, it's a logically different part of the story.
Okay.
A code defines a theory. Any theory can be put on any geometry. The same way like toric code can be put on any geometry. So choice of geometry is a sort of perpendicular direction to the story. You can choose it whatever you want.
I'm not familiar with the CFT to TQFT connection. Where did that? Oh, you're not talking about that.
I skipped that. I skipped that slide because
The previous slide, you had CFT equals TQFT after condensation.
Yeah.
Is that something I'm supposed to know about in condensed matter?
So I do not know what is known. It's part which is very well known is that TQFT is related to conformal blocks. Things I think we're adding is how to correctly combine conformal blocks to actually build a CFT. So this statement as it is, I think, is a new statement, at least cannot be found in the literature. Maybe known to experts in some way, but not found in the literature. So this is new. The fact that toric code can be written in terms of AB theory is fairly well known, but I will probably. Do we want to speak about that, or we want to talk about quantum gravity with an example of a toric? Maybe that will be more fun.
Yeah, let's do quantum.
Yeah, that's the quantum gravity. There's a generalization of all of this, and mathematically there is a way to explain that you can start with the classical code, go into quantum code, calculate the stabilizer state of that quantum code. That will be a CFT partition function, and then see that CFT actually can be obtained directly from the classical code by going through a lattice. All of that 2 ways. I presented mathematically the same. There is a way to see it, and the way to see it is through Chern-Simons, and I had a bunch of slides explaining that, but it's exactly the slides with this construction A emerging from anion condensation, and that's what we discussed in our most recent paper. If you care, please ask me. I will be more than happy to talk about it, but maybe it's not so much fun. Maybe the real fun is to talk about a little bit about anion condensation, how I understand it. So anion condensation is when you say, I want certain anions to act trivially. What does it mean to act trivially? It means that any Wilson loop made with this anion should act trivially on whatever Hilbert space which will survive after anion condensation. What I just did, I was trying in terms of words, manipulate the projector on the CSS code subspace. It means that I have certain set of anions, and the set of anions is a code, classical code. And then I consider all possible Wilson loops which are built out of this anion, and I sum over them, and I sum over them until I project on the space from which they act trivially. So yes. Oh, no. So this guy with the CA standing here in 0, this is like Z operators, and Wilson loops with the charge here in 0, these are like X operators. And if you rewrite that as Z to the power and X to the power, you will see that all I'm doing, I'm just building the projector on a code subspace of a CSS code. Okay, I looked at this formula for last 3 months, therefore for me it's exactly the same as X and Z. Now I realize for you it might be a little bit bigger barrier to recognize this. Maybe I should write that as in terms of X and Z explicitly. Oh, and actually there's a typo. This is psi C and this is also psi C, and this is a projector.
It's rank 1 projector, or
it depends on what kind of code you consider. Classical code. If you consider a self-dual classical code, it will be rank 1 projector. And that means that you condense the maximal group of anions. There is nothing else to condense.
So Lagrangian the maximum.
Exactly. Self-dual means very good. Exactly. Mathematically, self-dual code is another mathematical language to say Lagrangian subgroup, because a code is an abelian subgroup and self-dual code means it's maximal. So it's exactly Lagrangian. That's what we emphasize in our recent paper. These are 2 equivalent languages. Literally, just different communities use different languages.
But not all codes can be interpreted as some anionic excitation. Like not all errors act as anionic excitations for all possible stable codes.
Many abelian codes can, because you can start with different Chern-Simons theories, and therefore you can have very different alphabets of your codes. And I'm not sure if all of them, but it depends on the scalar product. If you're happy with the scalar product, then pretty much anything with a scalar product can be realized from Chern-Simons theory. So any favorite code you want, we can build it this way.
I mean, something non-locally connected, like not geometrically local.
There is no locality because those codes have no interpretation in terms of space. They have interpretation of charges of anions. They tell you which anions mutually commute with each other and which anions you want to condense. So these are code words are charges. They don't have spatial interpretation. Okay. All right, let's go into quantum gravity. I'll skip the motivation that people recently try to understand holography. Or maybe I should say that. Recently, people try to understand holography not as a duality between quantum gravity and a particular CFT, but as a duality between quantum gravity and an ensemble of CFTs. That's a conceptually different story. You have an ensemble of CFTs, and therefore, if you calculate something in that ensemble, that something will have variance. Any physical quantity you calculate in an ensemble will have variance. A geometric counterpart of that is wormhole geometries on the quantum gravity side. Okay, so and that's very interesting because it's a big deal in the quantum gravity story. You have wormholes, and now we can build all of that in the ensemble of code CFTs by considering different anions. And I'll skip this formula because I don't have time to explain it, but I will explain all of that in the context of toric code. Okay, so before we go back to 2 different CFTs in the context of toric code, I want to speak about topology. Can I speak for another 5 minutes, maybe?
Sure.
Yeah, that's okay.
Yeah, because people can leave.
Okay. So what did we do with toric code? We said we want to condense E, which means that E anion over any cycle should be trivial. We played that game. But now I want to play a different game. I want to play the game of topology. I have a torus, physically torus, double periodic boundary conditions. I want to say a certain cycle of a torus, I want it to be trivial. I want to shrink it. If I shrink it geometrically, it will be a handle body. I don't know what I had for breakfast today. a donut, it means that one cycle is shrinkable, another is not shrinkable. What does it mean a cycle is shrinkable? It means that any Wilson loop around that cycle is trivial because you can shrink it into nothing. So what I'm looking for, I am now looking in a particular cycle, which is a red one, let's say, and all Wilson loops, all anyons around the red cycle, I want to shrink, which means that I want the wave function invariant under both of these generators. What is that? It's yet another code. It's actually also a CSS code, but it's a stabilizer code generated by these two guys. And the corresponding state is simply this state. So this unique state is what survives if you shrink the A cycle. Can I also shrink the B cycle? Of course. For that, I need to write blue E and blue M, and then will be X, Y, and Y, X. And the corresponding state will be 0, 0 plus, 0, 1 plus, 1, 0 plus, 1, 1. That's the B cycle being shrunk. There is an algebraic way to explain it. Actually, the observation that shrinking A cycle as a stabilizer state goes back to a rather famous paper by Brian Swingle. I believe Brian was your colleague here at Maryland back then. It's a rather famous paper, so it's not an entirely new result. Putting it in this context has not been done, so I'm just doing this synergy here. I'm taking this idea and I'm saying, in the context of Kitaev code, there are three cycles. There is A, B, and A plus B. Normally, you can have any integer number multiplied by A plus any integer number multiplied by B. But since everything is mod Z2, there is only A plus B, A or B. There are only three cycles to shrink, and the corresponding states are these ones. What is the statement of a holographic duality? The statement of a holographic duality is that an average over code ensemble, I have two code CFTs. I have two condensable group of anyons, E anyon and M anyon. And an average over them is just weighting with the equal weight. The average over code CFTs is the sum over topologies. I shrink A cycle or B cycle or A plus B, or in fact, I need to go and try to shrink all possible cycles. And in that way, I will represent all three-dimensional geometries. The shrunk cycle is a three-dimensional, it's a donut. Donut is not a torus, donut is three-dimensional. So this is a donut of one geometry, another geometry, a third possible geometry. There is only three possible geometries. For Kitaev story code, it's a mathematically very simple way to see that a sum of this plus a sum of this is up to an overall coefficient is a sum of these three. I'll leave you at this simple calculation to do to convince you that this is the case. Okay, so
the psi and psi-m are I also condense.
Yes, E means you condense all E, M you condense all M, A you condense all red, B you condense all blue. A plus B means you need to multiply blue by red and condense that.
The different condensation subsets
Yes.
correspond to either the CFT side or the
Right, or the gravity side.
Gravity.
When I say condense, this is not a standard language because no one, we said that in our paper, but this is not a standard language. You cannot say you condense the cycle because cycle is a geometric thing. The proper way to say it is that you calculate the partition function of this three-dimensional field theory on a three-dimensional geometry where one cycle is trivial. You calculate it a partition function on a torus, excuse me, on a solid torus, on a donut, solid torus. It's a name of the three-dimensional geometry with one cycle filled with dome.
So this is must be some, if you're saying this is so super general, there must be some law about code switching. So condensation in computer science is code switching.
It's not code switching. What is that? What is that? Victor's asking, what is that mathematical? What is that mathematical? Can I give a mathematical theory? I'm coming to two last slides. Mathematically, it's not entirely simple. We can prove things, but explaining them in a simple way is a little bit complicated. But the idea is that you have a multi-qubit state, and in fact, you can take many tensor products of that if you want. And then you have a big symplectic group, which is like a Clifford group. it's essentially the Clifford group, except that Clifford group also changes the overall sign of your Pauli string. And this is just looking at the Pauli string. And then you have a modular group, which is a smaller symplectic group. And then you have an orthogonal group, which maps codes to codes. And in mathematical language, those two groups form a reductive dual pair within this bigger group. And then the statement is that if you average over this part, or you average over modular group, the results will be more or less the same up to a coefficient. There is a unique state, which is invariant in both of them. Okay, I will skip mathematical formulation of that statement. My time is up. I want just to show one more slide, which has nothing to do with my result, but it has math similar to this. And this is a result from quantum information theory. And I do not know if it's a famous work, but I think it's a very nice work by Ross, Nizami, and Walter, relatively recent. The idea they considered was very simple conceptual. They say, we want to consider qubits, and we want to consider G of them. And we want to sum over all possible stabilizer states, all possible. Not a subclass, but all possible stabilizer states. So we will sum over the whole Clifford group. Then we will consider 2n copies. I'm translating a little bit what they did, such that G and N from this slide will match G and N from my slide. They say we will consider 2n copies of this Hilbert space, and we will consider a sum over all possible stabilizer states to the 2 to the n power. This is something like a design, a stabilizer design, when you average over the Clifford group. And then they were working very hard to show that what you get is a sum over certain codes. They never formulated it like that because they somehow hesitated to call classical codes. But they say that there is a quantum code of a CSS type, and all you need to recognize that the codes of a CSS type are built from classical codes. So essentially, up to certain language things, I'm faithfully reproducing their result. Their math is very closely related. It's not literally the same, but it's very closely related and might be another instance of even more general mathematical statement. When a sum over codes is equal to averaging over symplectic group or a Clifford group, which encompasses that symplectic group. And,
well, before you had the two subgroups that form some nice subgroup of the Clifford group.
It still has. This is a smaller symplectic group.
Okay.
This is a smaller symplectic group. This group of people, the authors, also speak of reductive dual pair. There is a group here which is also orthogonal. It's a smaller symplectic group, sp2g. Both of them is a part of a bigger Clifford group, which is the Clifford group of this whole space. But they only average of a Clifford group of this space.
Okay, I'm happy.
So it's much, much similar to what we have. Okay, I think I have to conclude at this point, and I will actually go very quickly through conclusion. You saw that codes play an interesting role related to CFTs. If you care how they emerge physically, codes encode condensable anyons in your topological system. And then after condensing the anyons, you get the CFT at the boundary of that system. That's how the relation between codes and CFTs can be derived. And the quantum gravity part is akin to the story where you average over the Clifford group. This is not literally what happens in our story. We don't have the full Clifford group. We don't have the phases. We only have the symplectic part of the Clifford group. But the idea is that an average over codes on one side can be equal to averaging over other quantum codes on another side. And one side can be interpreted as the CFT side and another as quantum gravity. And you saw that even in the case of toric code, it gives some not quite trivial relation between E and M and then A, B, and A plus B. Okay, I hope I ignited your interest. And with that, I want to thank you.